Assalamu alaikum. So let's solve question number 2. Given E state for step input, so let's assume this is E state to be any value, and the root of the characteristic equation, let's assume it's general form, so minus beta 1 plus minus j beta 2 are given, and we have here the block diagram. So from the block diagram we can find the closed loop transfer function y over r, so this will equal k1 over s square plus k2s plus k1 k3. So from the block diagram we can find the characteristic equation to be equal s square plus k2s plus k1 k3. Now from the roots of the characteristic equation we can find the desired characteristic equation, which will equal second order system, so s square plus 2 beta 1s plus the magnitude square, so beta 1 square plus beta 2 square. So this equation must equal to this equation. So now if I compare, k2 will equal to beta 1, so here I'm having 2 beta 1, and we have k1 multiplied by k3 will equal to this one, so k1 k3 will equal beta 1 square plus beta 2 square. So we need another equation either to find k1 or k3, and this can be done from the y steady state. So y steady state due to step input is equal t of s at s equal to 0, which is the DC gain. This will equal t of s, and this will equal k1 over k1 k3, so this will equal 1 over k3. So y steady state is equal 1 over k3. Now y steady state will equal the r steady state, which is here the 1 minus e steady state. So this means that k3 is equal 1 over 1 minus e steady state. So here we have k3, which will equal 1 over 1 minus e steady state. So now we have k3, we can substitute it here, and we can find k1, which will equal to beta 1 square plus beta 2 square multiplied by 1 minus e steady state. So this will be the beta 1 square plus beta 2 square multiplied by 1 minus e steady state. Now to find the steady state error due to unit ramp, let's evaluate the error dynamic. So E of s will equal r of s minus y of s. So now E steady state will equal the limit when s go to 0, s e of s, which will equal the limit when s go to 0, s the input 1 over s square minus y of s r of s. So this will equal k1 over s square plus k2s plus k1 k3 multiply 1 over s square. So the s will eat one of the s's, those, and if we simplify, this will equal to the limit when s go to 0. This will equal s square plus k2s plus k1 k3 minus k1 over s square plus K2S plus K1 K3. So in order to have finite value for the error, this term must equal to 0, but we know that K1 K3 not equal to K1, which means that we know that K3 not equal to 1. Why? Because K3 is equal to 1 over 1 minus E steady state, and we are giving you a steady state value not equal to 0. If E steady state equals 0, this means that this term will equal to 0 and we have a finite error. But because K3 not equal to 1, this means that E steady state will equal to infinity. So here we have the infinity. Now for B of t, if we examine the signal B of t, then B of t will equal to K3 y of t. So this means that B steady state will equal K3 y steady state. And if you remember, we find that y steady state is equal 1 over K3, so this will equal to 1. So let's solve the last question with respect to beta. And here we assume only that beta is greater than 0. Now the first thing, we should find the closed loop transfer function, which will equal beta k over s square plus beta ks plus 3 plus beta k. Now we need to find k such that the system, the step response is underdamped, overdamped, critical damped. We know that omega n is equal square root of 3 plus beta k, and from here we can find zeta. So 2 zeta omega n is equal beta k. So this means that zeta is equal beta k over 2 omega n, which 3 plus beta k. Now we know that for the first one we have zeta greater than 1. Here we have zeta less than 1 greater than 0, and here we have zeta is equal to 1. So zeta is positive and omega is positive, which means that if beta is greater than 0, this means that k is greater than 0. And this also for the stability requirement. The system must be stable, and if we have a response critical damped, underdamped, or overdamped, this means that the system is stable. So now let's solve for the first one. So let's solve for the first case, which is zeta is greater than 1, which means that beta k over 2 square root of 3 plus beta k is greater than 1. Let's square the two parts, so we have beta square k square over 12 plus 4 beta k must be greater than 1. So this means that we have beta square k square minus 4 beta k minus 12 must be greater than 0. If we arrange it as a k square plus b k plus c equal to 0, so we can find the roots, which will be that 4 minus, so 4 beta plus minus the square root of 16 beta square plus 48 beta square over 2a, which is 2 beta square. So simply here we have two roots, so we have 4 beta plus minus this will be 64, so 8 beta over 2 beta square. So simply this means that we have the first root, we have k equal to the plus, so this will be 6 over beta, this is the first one, and we have second root which will be the minus, which is will be minus 2 over beta. So if we go here, the first root 6 over beta, this is minus 2 over beta. Now here this will be positive, this will be positive, this will be negative, but keep in mind we need beta, we need k to be greater than 0, so this is the range that we are interested in. So the first thing, this equation must be greater than 0, which means that k must be greater than 6 over beta. Now if we go for the zeta less than 1 greater than 0, this will give us beta square k square minus 4 beta k minus 12 less than 0, so we are tracking the negative. The negative is this part, so here k greater than 0 less than 6 over beta. Finally the equality zeta is equal to 1 at k equal to 6 over beta. So now we can write the value of the k when the response is under damped, so k greater than 0 less than 6 over beta. When the response is over damped, k must be greater than 6 over beta, and when the step response is critically damped, which means that k is equal 6 over beta. So now only substitute your beta here and you can get the range of k that satisfies the step response in the question. That's it.